So hi everyone, let's start another session here. So what my plan is in this talk is basically like raise some of the issues that you may encounter when you're training learning models of geospatial data and why they happen, right? So the plan is to switch between a couple of slides just to illustrate what these issues are. Then I will try to switch back to that second notebook we didn't have a chance to cover in the hands-on and just skim through some examples with actual code. So if you actually want to reproduce part of the presentation in your machine, it doesn't need to be now. The same notebooks we shared on Monday, they are already available on the JuliaEO 2023 GitHub repo, and you can follow with your own time later, right? So, first question here, which is the question that happens all the time when you're doing machine learning, right? So, I don't know if that has ever happened to you, but it's like pretty common if you're doing machine learning with geospatial stuff, which is the following recipe here, right? So you train your models using samples from a source domain. I'm calling here this domain in blue. So what happens here, right? So you have a geospatial domain where I'm splitting part of this domain into what I call source, D sub S for source, and another domain, D sub T for target. We will be training models in the source and trying to make predictions in the target, right? So you start with your workflow, you train your models in the source domain, and then you try to estimate which model is best, right? So you have a list of models, decision tree, logistic regression, whatever this model is. And the ways that we usually, let's say, rank models is by cross-validation, because you don't have access to labels in the target. So you take a cross-validation procedure in the blue area, and then you say, okay, according to cross-validation, my best model is model 1, whatever, model 2. You create this selection, right? You rank the models, and then you apply the model in the target, D sub T, and then you realize that there's a big surprise. Like you say, okay, my model performance is actually quite poor in the target, and the actual error is actually it's prohibitively high. And so why this happen? Like this happens all the time, and I reviewed like one paper recently that the same thing occurs, and every time I review a paper of machine learning in geospatial stuff, the authors rank models and they pick the one in the top, which is actually not the best model. And the reason for that is kind of understood. So this slide is a bit abstract, but I'll try to go over this illustration here so that you get the big picture. The intention here is not to go into the exact understanding of things, but just get an idea of what's going on. Imagine that I have like two images, Z1 and Z2, which are my covariates. So these are the variables that I'm using to train a model, right? So any image that you can imagine or something like this. I'm creating here this plot of this standard, let's say Gaussian, right? Everything is like just perfect. And then you see that this space gets deformed as you increase the spatial correlation, right? So you go from perfect circles to something that's completely like, it looks like what we call a manifold. And the problem with that is that like sometimes you're training in an area, because real world has spatial correlation, right? So you're training in an area that has like a shape like this, like a moon or a banana like this. And then when you apply your model, the banana is like this. Like you're from one region where the distribution has like some manifold, and then you go to another region where the model has not learned anything here, right? So you learn a bunch of relationships in this area, but when you go to the target domain, your banana is, let's say, flipped to some other distribution, and you completely lose the performance of the model. So this has to do with the fact that traditional models and methodologies developed for machine learning assume that your samples are IID, right? Like identically equally distributed, right? But when the samples have spatial correlation, which is the synthetic example here, you lose a lot of the properties of the models, right? So that's one reason why things fail. The second reason is shifts in distribution, right? So the first one is like just the fact that you have spatial correlation, you create these deformations in the feature space and you lose your performance in the target. The second is that like usually like in physical world, you have trends, right? So you have a physical process that, let's say, sediment deposition, or there is a trend of like a cold front moving from left to right. And so you have areas with higher values of some covariate and areas with lower values or something like this. And if you train your model here, and if you think of the covariate distribution here, it will have some given distribution here, but if you go to another domain, it will be shift to the right, for example. And this is called dataset shift or concept shift or whatever shift there is. There are many names for the same thing, but it's basically saying that the source and target distributions, they don't match. And because of that, again, you are training something in distribution A, and when you want to make performance predictions, you go to distribution B, and things just don't work anymore. So I'll try to switch to the notebook to show, let's see if it works here. Some of these things live, right? So this notebook, let me share the full screen. Share the screen one, I guess. And if you go to, let me stop the presentation. Yeah, so if you go to this notebook, which is the one that we already have access in the hands-on session of Monday, you can follow some of the steps here to see these issues actually happening, right? So the first example here is the example I just showed in the slide. Let's see if the visualization is gonna load here. I should have loaded this before, yeah. So you see these are the same example I showed in the slide. So this is an actual Mackie visualization. I should be able to zoom in and zoom out, but I don't know if it's responding. My tablet's not very responsive. But so you have a source region here. Oops, too much. You have a source region here where it's just like have a collection. Man, Mackie. You have a collection of pixels. Let's just reset the thing. You have a collection of pixels with labels, which are these blue ones, and you have a collection of pixels that we want to make predictions, right? So if you do this, just ignore this error warning here. If you do this procedure with cross-validation, what happens? You get this source domain, you break it down into smaller subdomains, 1, 2, 3, 4 in this illustration. You hide one of them, you train the model, and then you predict the error in the one you've hidden, right? So everything is concerned with your source domain. The target is completely outside of revision at this time, and then you just estimate this error of the model age as this average of errors at each of these subblocks here, right? So you say, for the jth subdomain of the source, I estimate some sort of error, which is based on this loss function. So you take a loss function over the prediction of the model and compare that with the actual label you have on that domain, and you create this estimation of error fully based on your source. And then what happens is if you go down here and you look at the actual result, you see that the predictions in the left, let's see if I can zoom here. I'm always against the correct direction, so let's go here. So if you zoom here very closely, you see that many predictions were like incorrect just because the model was not aware of the geospatial location of the samples, right? So you have yellows inside of the black and all this mixed up prediction just because this is the actual label, right? Just because the model has explicit saying about like where the coordinates are, right? And if you see the error that you estimated with cross-validation is about 2 times higher than the actual error that was expected, right? So the error that you get when you apply the model in the target is 2 times higher than the error that you estimated with cross-validation. So that's very dangerous for deploying models in the real world, because you think your model is good, then you change the area to some other area, just screw it up.
Julia?
Yeah.
Can I make a question?
Yeah.
Did you take the coordinates into the model? For
No, just
okay.
the covariates, just the
Okay.
covariates, yeah.
Yeah.
And so the explanation, again, let me just take the guy out here, yeah. The explanation, again, is similar to that illustration I showed before, but the cross-validation procedure, the naive one you have in scikit-learn and all these frameworks for doing machine learning, they are random splits of the data set, right? So you get your domain, and you randomly select samples to be in fold 1, fold 2, fold 3, fold 4. And by randomly selecting folds like this, you get in this situation where fold orange, fold red, fold green, and fold yellow, they are spread everywhere, because this is a random sampling. And because of that, when you hide fold red to use as your hidden fold, and you train the model with the rest, we will always have a sample that's too close to fold red. And because they're too close and there is spatial correlation, you'll be kind of leaking information to red, and you have over-optimistic error assessment, right? So that's what is causing that expected error to be like much lower than it should actually be. So there are alternative methods for that, like in the literature. So it's pretty much this umbrella of geostatistics, right? So you have other methods in the literature that try to create estimations of error that are more conservative. For example, block cross-validation. You take your source domain and you split it into these blocks. And the idea here is that you're going to hide one of these blocks, and you create this thing called the dead zone, where you cannot use samples from here in your training. You train with everything outside, and you predict in the red. So that's just a virtual, let's say, way of removing the correlation length R that you specify a priori from your estimates of error, right? So you repeat this process block by block until you get an estimation of the error. And here's the equivalent of leave one out, right? So instead of just hiding one sample to make the error estimate, you hide the sample and you also hide a radius R around the sample, and you repeat that. And so the good news is that these are very tricky to implement for arbitrary geospatial domains, but geostats.jl has all these implementations in parallel, so if you need to do this kind of stuff, it's already there, right? So that's the code you actually need to execute to get these estimates. So up there you see there's a classification task where I'm saying I want to make predictions of the crop type based on 4 bands of the satellite. So there's a table, this is a table with 4 bands, and the target is the crop. It could be a raster image or it could be anything, but you're just defining the task that you want to perform. You define your learning problem. In this case, it's going to be this geospatial learning problem where you have the source domain. I've been calling D sub S here, but it's omega sub S in the code. You have the target domain, and you have the task. So this encapsulates all the information you need to perform the training and prediction, right? After that, you can load any learning model from the MLJ stack, which is the Julia stack to load basic models from, let's say, all scikit-learn models are currently supported, plus other models implemented in Julia directly. So you have more than, I don't know the last number, I think 108 models. It's like a huge number of models. And here I'm loading the decision tree. And after you load the decision tree, you can wrap it up into this strategy here that I'm calling pointwise learn, which basically says, okay, that's going to be the naive way of applying the model. You just go pixel by pixel making predictions, or pull all these pixels into a big table and make the prediction. But there are possible alternative ways to do that. Here you're choosing the misclassification loss as your estimation loss, right? And then you create the procedure, which is block validation. We changed name in the latest release, but you can find that in the documentation, where you specify the radius R that I illustrated in the illustration, and you specify the kind of loss for the target variables, right? I'm saying, okay, for the crop variable, I want to estimate error with misclassification, because it's a misclassification problem. Then you can call this function error of the learning strategy on the problem with this method, and it will return a dictionary with all the errors for the targets, and I'm just taking the result for the variable crop. And here is what you actually have in terms of predictions, right? So if you actually do the naive error estimate, you'll see like the actual error estimate, which is the actual error you get, like you see that these two values here are much closer now, 0.23% misclassification, because you are using this radius 30 to avoid that over-optimistic error estimation, right? Another reason why we think it's important to start embracing this idea of doing geostatistical learning and not machine learning with geospatial data is that you have ways of designing new models and new algorithms that are more adequate for geospatial data, right? So you're not just taking a toolbox that was designed for tables, applying to geospatial and pretending it will work. You actually start to think actively about how to actually develop new models for geospatial data. So here's another example where you have an image and you want, for example, to segment this image into subdomains, for example, right? And that's usually an important step in modeling because nature is super complicated. You want to break the distribution into a mixture model where you have subdomains to model separately. And one way that you can do that when you don't have labels is via clustering, right? So you want to do some clustering in this image, but you see that if you apply normal clustering methods like k-means or any algorithm like that, there will be no constraints on how these clusters look like spatially. So you're just looking at the feature space, the colors of the image, and because you're just looking into the feature space and you don't know where the sample is coming from, you'll be like getting these clusters that are everywhere. They're just spread everywhere, right? So you have a cluster of yellow, but yellow is everywhere. You have a cluster of black, a cluster of blue, and so on. And so what we do is we develop new clustering algorithms that allow you to at least play with hyperparameters to control this spatial continuity, right? So there's one algorithm is called SLEEK. It's adapted from the image processing literature. It's called simple linear iterable clustering. It's one algorithm where you have a measure of distance, which is just a distance in the feature space combined with a distance in the physical space. And you have this hyperparameter m that weights which is more important, right? So if you play around with m here, you get clusters that are more continuous or more focused on the features, right? So this is the kind of thing that we try to work on, and Geostats has, I think, 3 clustering methods that are specific for geospatial data. We have SLEEK, GHC, which is geostatistical hierarchical clustering, and GSC, which is geostatistical spectral clustering. And all these algorithms are being designed for geospatial data from scratch. They're not, again, traditional algorithms to apply in geospatial data. They are algorithms designed for geospatial data, right? So after like many years developing this framework, the Geospatial framework, we came up with this paper, which was the paper where we tried to formalize some of these ideas and concepts, right? So it's a bit heavy on the notation and stuff, but the concept is super simple, right? So what is geostatistical learning, what we've been calling here, right? So geostatistical learning is when you have, again, all these elements that I was describing. You have a source geospatial domain, D sub S, and you have a source learning task, which is classification, regression, or anything like this. You have a target domain, D sub T, and a target learning task. And geostatistical learning consists of learning this task over the target domain, using the knowledge that we acquired while we're learning the model or the task TS in the source domain. So all these things are more explained in the paper, so if you need to get more, let's say, ideas of what's going on, if you want to chat after the talk, just come and we can nail down what these names are. But what we actually can do when we start to talk about these things very abstractly, because we define the elements very clearly, we can build learning models that are super sophisticated. Like, I mean, I don't know of any other framework in any other language that allow you to do these kinds of things that we are doing here directly. So here, I'm loading a building model, right? So you see this is like, my tablet is kind of dying to just visualize this thing, but this is like a building with complicated geometry. So you see triangles, quadrangles, whatever. And I want to do machine learning on top of this thing. So this is my mesh where I loaded a building model. Say, imagine you are loading a volcano or a coral reef or something from earth sciences or something that you are interested in your research. What we want to do is to basically create a pipeline that targets these things directly, right? Without having to do a lot of manual work. So for example, if you participated in the hands-on session on Monday, you know how to do the geodata science part, which is creating features, for example, on top of your mesh. So here I'm creating a table of features where I'm saying compute the area of all the elements in the mesh compute the perimeter of all the elements in the mesh, compute the maximum inner angle of all the elements in the mesh. These are 3 features that I created on the fly, and I'm attaching these features to the mesh with the georef function, and this creates this geospatial data set where you see like triangles as geometries and 3 new features created just now, right? Now I want to visualize this. It's the same code as we had before, right? So I have these Mackie ways of visualizing, right, this domain. So I say visualize the domain of my data, coloring by the area. So that's the first one here. So if you zoom here, you see that these elements are colored by area now. This one is colored by perimeter, and this one is colored by maximum inner angle. So I've created 3 features on top of this geospatial domain. You can imagine like a satellite image or a 3D volcano model, whatever that is. And now I want to, for example, create like a training and a test set, right? So artificially what I'll do here, I'll just like split this geospatial domain into 2 pieces. And for that, I'll just choose a threshold tau, which I will apply to perform a group by operation. So I use that transform operation on my geospatial data set to create a group column, which is just wherever the perimeter is greater than threshold, group 1, wherever it's group 2. And then I'll just, for the sake of like example, I'll create a new column that's called stress, which is 1 over the area of the element. Just like saying like I have a force of unit 1. And then I created these 2 new columns, right? So you see here I had area, perimeter, and angle. Now I have group and stress. And what I can do now is group by this group variable, right? So I'll group my building by the group feature. This will create 2 subsets, the source and the target, as I'm calling here as a geospatial partition. And I can plot the 2, right? So I can just come here and say visualize the domain of the source with the color royal blue, and the domain of the target with gray, right? So if I zoom here, I subdivided my domain to elements that are in group 1, and here are, let's say, the pieces of the building in group 2. Now I want to train the model in group 1 and predict in group 2, right? So what I will do, I will just follow the same recipe I've shown above. So I'll create a regression task that maps area, perimeter, and angle to stress. I'm just creating this synthetic example, right? And I'll define my geostatistical learning problem that trains in the building parts that are in group 1 and predicts in the building parts in group 2. And that's the task T that I specified. I load again a decision tree, create this strategy to just learn point by point and solve. And this creates my estimated building with stress, right? So I can just go here and plot the actual value of stress that I've hidden, right? And the value predicted by the decision tree. As you see, like the colors are different, and that's to, again, emphasize that if you just apply these models that are not designed for geospatial data, and you apply it point by point, you don't do anything extra, you fail to capture this geospatial information here, which is volume, right? So when you train a model that you have a variable that's measured, let's say on 1 kilometer scale, and another pixel is like 10 kilometer scale, these are different things. The process is averaged, right? So just training a model like blindly like this without considering the size of the pixel or the size of the elements, you're going to be biasing your answer to something else, right? So that's what I created this example just to show that we need to customize these learning models even more. Like we need to create new models that take this support information into account. So there are some challenges in terms of research and in terms of technology that we're trying to address over the years, and we got a lot far already, but there are many things to do still. For example, we want to take into account the fact that the distance that we compute should be geodesics, right? So we're not computing straight lines. Sometimes these models are very curved. We have geometries that are curved surfaces, and in order to compute geospatial correlation, for example, we would like to follow the distance along the curve and not straight lines. This also is related, as I mentioned, to adequate correlation structures on manifolds, because correlation behaves differently when you have curved surfaces, so you cannot just assume that you can compute variograms and correlation functions as you usually do with flat 2D maps, right? So there are challenges, mathematical challenges in that direction. And specifically, if you talk about the climate and all the challenges we have in global scale, I think we want to also target some of these learning models on the sphere directly, right? So treating the sphere as like a curved geometry with specific topology and so on and so forth, and designing learning models on top of this object instead of just flattening out into a projection system and working there and coming back. I mean, I have a lot of more to say about these things, but I'm currently, as I say, I'm currently working at this company, Arpeggio, that I founded a month ago, where we are trying to evolve this technology even further with client use cases. So if you have any case and any interest in developing these things further, just reach out at this email and website. So feel free to contact. And if you have questions or anything, just feel free to ask as well.